Good morning, everybody. Today I'm going to be talking a little bit about different ways that you can express the arrangement of electrons around the nucleus of an atom. Now, prior to this, I've had you color-code the periodic table, and that periodic table looks something kind of like this without the terrible, terrible glare. We're not looking at that side, we're looking at this side back here. And in particular, what we're looking at is going to be these markings I made in here with like 1s, 2s, 3s, 3d, etc. So I've also given you a couple new pieces of equipment today. This one right here is what I'm going to refer to as the arrow diagram. And I'd like you to make a small note at the top of that. Basically, that note consists of the word start. So we're going to start right here. I'm going to work some examples of what we're talking about, and then we'll take a look at some of the ones that you have. Basically, the four types of notation that we're going to be spending our time on are what's called an orbital diagram, an electron configuration, a noble gas configuration, and a Lewis dot diagram. Okay. Different ones have different strengths, and some are much easier to find than others, depending on if you've got an annotated periodic table, which you all have. But we're going to start by talking about the orbital diagram. So, for the orbital diagram of sulfur, what we're going to do is we're going to start off by figuring out, okay, what is sulfur's atomic number, and therefore how many electrons am I going to have to find homes for? Okay. So I look on my periodic table and I see that sulfur is element number 16. And so I can say for sulfur that it's going to have 16 electrons. So I have to find homes for 16 electrons, and in the orbital diagram, I'm actually drawing those homes, those spaces, I'm representing them as little squares. Now, before I go any further, I want to show you all this. This right here is a representation of what different orbitals actually look like. And I guess I should probably back up and define what an orbital is. An orbital is a three-dimensional region of space located around the nucleus where electrons are most likely to be found based on the fact that when they're in these three-dimensional regions of space, they are the most stable. They've got the lowest amount of energy. They are nestled in as close to the nucleus as possible, but still far enough away from other electrons to where they're not feeling awkward. And so you've got S, and S sublevel has a single orbital in the shape of a sphere. Okay, that's why we call it an S sublevel. P sublevel has three orbitals. This one, and this one. Each one of these can hold a pair of electrons. So 2 electrons can go into an S sublevel. 2 plus 2 plus 2 can go into a P sublevel. Why do you think they call this one a P? What's the shape there? Is it a parabola? This is the first you're hearing about this? Okay, you've heard the word?
Yes.
Or else to fight.
I have no idea.
Okay, alright. So it's in a parabolic arc, and that's, it's not a parabola. Oh, there we go. And then you've got D sublevels. A D sublevel has a total of 5 orbitals. Each one of these orbitals down here, 1, 2, 3, 4, 5, can hold 2 electrons. The D, I believe, comes from the fact that it's like a double parabola. Because if you look here, it's almost like a little cloverleaf shape. So you've got a cloverleaf here, another one here on a different axis, another one over here, another one over here, and then you've got this weird green thing with a couple blobs coming off of it here in the middle. And then the F sublevel has a total of 7 orbitals. I don't even know what the F stands for, and I'm not even sure what the math is involved in all that. But the important thing to note is that each of these 7 orbitals down here can hold a pair of electrons. So if I'm looking at total numbers of electrons that can fit into each of these different sublevels, S sublevel has 1 orbital, so it can hold a total of how many electrons? 2. 1. 1, 2. Remember, we're using little arrows to symbolize electrons. P sublevel, it's got 3 orbitals, so it can hold a total of how many? 6. And go 1, 2, 3, 4, 5, 6. Why did I come back and hit 4, 5, 6 after I did 1 each and 1, 2, 3?
Because they spread out before.
Does anybody remember what rule that's called?
Something about men's toilet.
Guys in the bathroom rule, okay? That would be Hund's rule. Okay? And it is important that you know the names of these, so be sure and go back and check out those notes. So it can, okay, so an S sublevel can hold a total of 2 electrons. P sublevel can hold a total of 6 electrons. What about a D sublevel? Okay, it's got 5 orbitals in it. Each one can hold 2, so let's count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So D sublevel can hold a total of 10 electrons, 2 per orbital. How about the F? 14, exactly. And so it can hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now you may notice that my arrows are getting kind of derpy there. Sometimes whenever you're doing diagrams like this, the correct way to do it is nice, neat arrows like that, but chemists tend to get in a hurry, and so they just do the arrows with like a little half head on them because it's much faster to do several of those in a row. Okay? You can do whichever kind you want. I'm not going to be picky about your arrows. It's not a big deal. And so the F sublevel can hold a total of 14 electrons. Now, take a look at your periodic table. The region on your periodic table here on the side is referred to as what? How wide is the S block? How many electrons can an S sublevel hold? What do you call this chunk over here? How wide is the P block?
6.
How many electrons can the P sublevel hold?
6.
What's this in the middle here? B block. Without counting, can you tell me how wide it is? Probably 10. Because the B sublevel can hold 10 electrons. And this one here is the F block. Okay? It's 14 wide because it can hold a total of 14 electrons. The shape of the periodic table comes directly from this right here. Okay? Is this making sense? It gets better. Okay? So, like I said, getting back over to our orbital diagram. So, we decided that sulfur has a total of 16 electrons we need to find homes for, right? So, what we're going to do is we are going to follow this arrow diagram right here. Figure out, let me see if I can move this around a little bit. What order we're going to fill these in. And we can do this with the arrow diagram, or we can do this just with the periodic table. But the first thing we're going to do is we're going to start where it says start. The first ones we come to is 1s, right? Okay, so I'm going to draw myself an orbital, and you can draw an orbital either as a box and label it 1s, or a blank and you can label it 1s, or a circle and you can label it 1s. It is largely up to you and your personal preference which one you use.
On this paper?
On this paper. Well, on what we're going to show you. Okay. So for this first one, I'm just going to use boxes. So I'm going to come up to my sulfur, and I'm going to start by drawing a box to show my 1s orbital, and I'm going to go ahead and drop 2 electrons in there. So there's 1, 2. Okay? So, 2 down, how many left to go? 14 more. So I'm going to follow my arrow diagram. I've gone from here through here. Now I'm going to come to my next arrow going down. What do I run into? 2s. So now I'm going to draw myself a box and call it 2s. How many electrons can go in there? 2. There's 1, 2. Okay, so 4 down, how many left to go? 12 more to go. I go to my next arrow. What do I come to? I come to 2p. Okay? Now, the p sublevel has a total of 3 orbitals. So I'm going to draw myself 3 little boxes. I'm going to label the entire thing 2p. Now, what order do I fill these in?
You have to put one each.
1 in each. So 1, 2, 3, 4, 5, 6. So how many total is that? That's 12 total, right? How many left? 4 more to go. So, following my arrow, from 2p, what do I come to? 3s. And s sublevel just has 1 box in it. So I'm going to come up here and I'm going to draw orbital for 3s. And sink a couple more electrons in there. So that's 14. How many left? 2 left. So I'm going to come from, I finish this arrow, I go to my next arrow. What do I come to? 3p. Again, p has a total of 3 orbitals, so I'm going to draw myself 3 more boxes. Label them all 3p. Now I've only got 2 electrons left, right?
You put one.
One's going to go there.
And then one in the second one.
One's going to go there. Okay? That is my orbital diagram for sulfur. Now I want to show you something cool. When you find sulfur on your periodic table, not that side, that side there, according to your color code, what energy level is sulfur in? 3. What block is it in? Did I count my electrons wrong? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We need to do 16. I am so sorry. So we need to do 2 more. So there's 15. There's 16. That's the orbital diagram. Disregard what I said a minute ago. So I've got a total of 4 electrons in my 3p. You see that? I find sulfur on the periodic table. It's in energy level 3, which you can't see there. It's in the p block. And how far over in the p block is it?
4.
So there's 4 electrons in my 3p, and that's how this ends up. Okay? Questions? Where do I start? Is this making sense? Or are you kind of like, I know there's something there, but I don't quite get what yet? Is that anybody? Or is it making perfect sense to anyone? Okay. So, that's the orbital diagram. Now for the electron configuration, which is right next door here, we're going to do exactly what we've done with this, only we're going to do it without drawing a picture of all those little boxes and arrows. So I'm going to scoot this over just a smidge so I can still see what I'm doing. Give myself room to work there. And so I'm going to go in the exact same order that I went in. 1s, 2s, 2p, 3s, 3p. But instead of drawing arrows, I'm going to say 1s. How many electrons are in my 1s?
2.
That's 2. That 2 is a superscript. What's next? 2s. How many electrons are in 2s?
2.
Okay. Next I have 2p. How many are in 2p?
6.
Uh-huh. And I come to 3s.
2.
Uh-huh. And then 3p.
4.
And that's an electron configuration. Okay. Now, you can do all this without using the little arrow diagram. If you have a little arrow diagram, you know, if you feel more comfortable using that to make all of this make sense, then that's great. Let me move my little arrow diagram back over here. We might add a couple more things to the arrow diagram, if you'd like. It's taking forever. You might, either up in the corner where you've got space to do it, you might go ahead and just make yourself a little thing saying that S has 1, a P has 3, a D has 5, and F has 7. So whenever one of these is full, an S will have 2, a P will have 6, a D will have 10, and an F will have 14. Now I'm going to show you how you can go straight from periodic table to the electron configuration without having to draw these orbitals at all. Okay. Okay. So let me zoom back out and let's take a look at my periodic table of shyness. Okay. Y'all see that all right? Okay. So I'm going to just start at the top, and I'm going to go through each of these sublevels as I come to them. Starting up here with hydrogen, what do I have? 1s? Okay, 1s is full, so that's going to start me off. Let me give myself a piece of scratch here. My 1s is full, that's going to be 1s, 2, 1, 2. Next row I come to 2s. When I get to the end of that, there's 2 of them there, so it's going to be 2s. 2. And I'm going to come over here across the gap to 2p, 1, 2, 3, 4, 5, 6, and I'm still going, so 2p6. Now I'm going to come down to 3, there's 3s, I'm going to hit 2 right there, and I'm still going, so it's going to be 3s2. Now I'm going to come to 3p, and it's 1, 2, 3, 4. Let's get over to sulfur. So for this, I'm just going to write 3p4. And I'm done. Great place for a question if you have one. It would probably help if I would do a little better job of describing actually what's going on and where around the atom these electrons are ending up. I'll draw you a picture of that here in just a minute. Before we do that, I would like to look at the other 2 types of electron notation on here. The next one on your paper is what's called a noble gas configuration. So if you'll imagine, you've got your sulfur atom. Okay, so in your nucleus, you've got a total of, sulfur is atomic number 16, so you've got a total number of 16 protons and however many electrons are in the middle. That's not that important, okay? You come to your first energy level. Here's energy level 1. And so in energy level 1, we've got sublevel S. So here's 1s. It holds 2 electrons. Here's 1. Here's 2. Okay? With me? Okay. Then we come to energy level 2. Energy level 2, roughly spherical, has got an S sublevel, 2s, 3, 4, and it's got a P sublevel, 2p, 1, 2, 3, 4, 5, 6 electrons in it. So You've got 2 in the first main energy level, 8 in the next main energy level. Now at this point, just going as far as 2p6, energy level 2 is completely full, right? Energy level 1 is full because it can only hold 2. Energy level 2 is completely full because it can only hold a total of 8. Right? So, at this point, if I stopped right there, if I ignored the 16 electrons in the middle and I just looked at the electrons that are there, what element would I be looking at? What? I'd be looking at neon. Neon has 10 electrons. It's got a full set in its first energy level. It's got a full set in its second energy level, right? And so you can make the argument that when we move on to that third energy level, which is going to come out here, it's going to be bigger, we're going to come to energy level 3, which is going to be 3s that has 2. And then in my 3p, it's only going to hold 1, 2, 3, 4, right? So, if you look at what's on the inside of this as being basically the same electrons that you would get with neon, with a few other electrons added on, we can note that on our paper, if I can get all of these in one place, I'm not going to try and do all this in one place. We can note that on our paper by saying that all of this in here is just like neon with this other stuff on the outside. So I'm going to put neon in brackets. And I'm going to add 3s2, 3p4. And that's what's called my noble gas configuration. It's like a shorthand. Because when you're looking at the electrons in an atom and you're trying to determine its chemical reactivity or why it's in a certain place on the periodic table, the only electrons that matter are the electrons that are in your highest main energy level. In this case, it's energy level 3. So we don't care about all these other electrons that are in here because they really don't do anything. Let's see if it will. Nope, it won't. Sure. They really don't do anything when it comes to chemical bonding. It's just these on the outside. Okay, do you remember what the special name is for the electrons that are on the outside? Valence electrons. Valence electrons determine an element's reactivity. And so all I'm really worried about are these 6 electrons that are on the outside. Okay? Now because these have 6 electrons on the outside, they are placed in group 16 on the periodic table. Look up at the top of group 16 of the periodic table that you have annotated. You've got an X up there. And it's got a pattern of dots on it, right? Okay. Right, so it's got 2 pairs of dots and then 2 single dots, just like that, right? Okay? Now, let me re-expand these valence electrons and show you their orbital diagram one more time. For just these right here, we've got 3s. This time I'm going to use a blank instead of a box. Then we've got 3p. You know where I'm going with this? There's a pair of dots. There's a pair of dots. There's a single. And there's a single. Or we say unpaired electrons. Make sense? So, that very last column you have on the paper, which you guys don't have the very last column on your paper, I was looking at mine. This right here is what is referred to as a dot diagram or a Lewis. That's not what a W looks like. A Lewis dot diagram. It just shows you the valence electrons and it shows you whether they are together in pairs whether they are unpaired. Because whether they're paired or unpaired determines how this element will react. Do you remember from the goofy element video, in order for an atom to be stable, it needs to have a full set of valence electrons, and usually that number is how many? Talk louder? It is 8, exactly right. If it's a full set of 8, you are stable, you're good. This one right here still has space for how many? We could put another one there, another one there. And so in order to become stable, sulfur is very likely going to steal electrons from somewhere else. When it steals 2 electrons and steals those 2 negative charges, it won't be a neutral atom anymore. What charge will it have? If it takes in,
Negative, right?
right, if it takes in negative charges, it becomes more negative. Because it will have more electrons than it will protons. Negative how many?
Negative 2.
What's written up at the top of that sulfur column?
Negative 6.
Uh-huh. So then it would become sulfur minus 2 ion, or sulfide ion. Okay? I'm actually jumping way ahead here, but I want to show you how it all ties back together. Because we're going to be taking running leaps going forward from here. Now, we're going to work some examples on the paper that I gave to you, so nobody panic if you don't quite completely, totally get this yet, but does anyone have any questions? So for each one of these, we're going to need to draw the orbital diagram, the electron configuration, the noble gas configuration, and the Lewis dot diagram. Let's start off with magnesium. On your periodic table, find magnesium and tell me what is its atomic number. Atomic number is 12. So we're talking a total of 12 electrons we're going to have to find homes for. Now, let's go ahead and use what we know about the periodic table, and let's make a prediction. Where are my last electrons going to end up? What kind of sublevel and what energy level? Where? And it's the second one over. Right, we're probably going to be ending things with 3s2. So I'm just going to kind of put that in a little thought bubble here. Because if I end all of my stuff with 3s2, I will know that I have done things right. Okay? So, let's set the periodic table aside and let's get the arrow diagram. Alright, so we start off, we've got a total of 12 electrons to find homes for. What's the first sublevel we're going to come to? Okay. Alright, I'm going to use circles this time. If I can. Call it 1s. How many electrons go in there? 2. Okay, there's 1, there's 2. Alright. What comes next?
2s.
2s. Okay. S only has a single orbital in it, so here's 2s. There's electron 3 and 4. Coming over to my arrows, what comes next? 2p. P's have got 3, so I'm going to go series of 3 circles. All together are going to be 2p, so there's going to be electron 5, 6, 7, 8, 9, 10. Still have 2 more to go. So what comes after 2p? 3s. 3s. 11, 12. So there's my orbital diagram for magnesium. Now we can go straight from there and we can get an electron configuration, right? We just take all of these and we express how many electrons each one has with a little superscript. So it's going to be 1s, 2s, not 3p, 2p6, and 3s2. Alright? Now, if we want to figure out the noble gas configuration for this, you might need to look back at our periodic table. Okay? Say again? It is going to be neon. And you can do that by backpedaling. So we're going to backpedal from 12 to 11 to 10. So 10 is the last noble gas we came to, and that was at the end of 2p. So everything up through 2p6 is going to be replaced by neon. So I'm going to bring this down here. I'm going to replace all of that with the element neon in brackets. And everything outside of 2p6, I'm going to go ahead and write. So I'm going to write neon 3s2. And the only thing I still need to do is my dot diagram, which is just going to be these electrons right here. Up here, are they paired or are they single? They are paired. So I'm going to write, instead of an X, I'm going to use the element's symbol for magnesium, which is Mg. And I'm going to put a pair of dots on one of the four sides. It does not really matter which side. Those two dots are my two valence electrons. And I'm done. Excellent place for questions. Okay. We've still got some time. You want to do another one?
Sure.
Okay. Let's see if I can find one that's a little bit bigger and beefier. So we'll skip phosphorus. We'll skip calcium. I'm going to go all the way over to Krypton, because Krypton, we see something very interesting. I wanted to be sure I mentioned this, and I'm glad we've got this chance to. So element Krypton, find it on the periodic table. It's element number 36. So we're going to have to find homes for 36 lonely electrons. Looking at my color-coded periodic table, what energy level is Krypton in? It's in energy level 4, and it's in 4p, and it's the sixth one over. So we're going to think 4p6 in the back of our head, and if stuff ends with 4p6, we'll know we've done it right. Okay? Let's come to our arrow diagram. Let's see what we do with that. That's kind of out of the way. All right. So, where do we start with on our arrow diagram? We start with 1s. I wish I had a better screen. I'll just do another flip. Okay. We start with 1s. All right. 1s holds 1, 2 electrons. What comes next? 2s. 3, 4. What comes next? 2p. Okay. Let's put you up here. That's great. That works. And P has a total of 3 orbitals in it. So line, line, line. 2p. Okay. 4, 5, 6, 7, 8, 9, 10. Okay, after 2p, what do we come to? 3s. Let's just have one orbital. So 11, 12. What comes next? 3p. 3p, so we have 2, 4, 10, 11, 12, 13, 14, 15, 16, 17, 18. Not there yet, right about halfway there. Now what comes after 3p? 4s. So 4s, again, has 1. So that's 19, 20, right? So at this point, if we were building elements, we would be out to the element calcium, which is element number 20. Now what comes right after calcium? Scandium. Now, what is it labeled on your periodic table?
3D.
3D. So we're going to come to the first of our D sublevels. And D's have 5 orbitals. So I'm going to come down here and put 5 blanks for 3D. So here's 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. My D is now full, so it comes out to 3D.
4p.
4p. These have 3. Here's 4p. Okay? So, 31, 32, 33, 34, 35, 36. Where did we say we'd end up?
4p.
With 6, and we did, right? Okay. So now, now we're going to go ahead. I'm going to do the electron configuration down here. And it's just going to be all of these with a superscript instead of a drawing. How are we doing on time? I don't have it out here. So it's going to be 1s2, 2s2, 3p6, 3s2, 3p6, 4s2, 3d10, 4p6. Okay? Now the good news is this already is a noble gas. So if we want to just symbolize a noble gas notation like that, we can. We can get away with that. Now for our dot diagram, super important that you notice this. We are just looking at valence electrons, right? What is the highest main energy level that we fill? 1, 2, 3, or 4? 4. So we are just looking at the electrons in energy level 4. What about these here? They're back down in level 3. They're not in your highest energy level. And there's a reason for that, and we'll talk more about it later. We don't have time to right now, but we were just looking at these 8 electrons here. Now, what do you notice about how they're set up in their orbitals? They are all paired. So I've got 4 pairs of electrons. Pair up top, pair over here, pair down here, and a pair right here. It's got a full set of 8, which is what makes it a noble gas, because it's stable and it does not react, because it doesn't need to. It's got all the electrons that are going on. And thank goodness that's going to bring us to the end of our notes today. Does anyone have any last minute questions, comments, remarks?